So I'm trying to get back into doing the rest of my AP Physics 1 videos. Ran into a few glitches with this Corona thing and my setup process here, but I'm going to try and knock out what I cover in Unit 6C. Unit 6, I cover system of bodies. And in 6C, I talk about momentum. And this is really the first time. I kind of briefly mentioned momentum earlier in the year, but this is the first time we really get into it. And it's just the way that I cover the information. Now, keep in mind, I always ask for definitions of momentum because everybody has heard of it, but not very many people are able, really no one gives me a proper definition. But they give me definitions that are good. They give me definitions that are either a force or an energy. And I get that because momentum is a little bit of force and it's a little bit of energy. And just keep in mind what momentum is. It's a property a moving body has. Property of a moving body. And, well, that's what energy is. That's what kinetic energy is. Momentum's a little bit like kinetic energy. A force is what gets a body moving. Momentum's a little bit like a force. And so I see those ideas. And momentum is just another different type of quantity. And I don't even think Newton was really truly able to get a good definition of momentum other than it's a quantity of a moving body. Let's think about Newton's second law. Now, most of us are familiar, or most people teach it as F equals ma, and then some people, you know, I like to stress its acceleration is net force over mass because acceleration comes from the net force. But actually, Newton's second law, it's not that at all. What Newton's second law, it relates the net force to a change in momentum. It relates the net force to how fast momentum changes. From this, we get F equals ma. But I think this is an important idea because if the net force is 0, then that was because we had no change in momentum. And this gets into the idea of conservation of momentum. And this is true. This whole idea is true for a single body and a system. This is why I don't cover momentum until I talk about systems, because you have to have multiple objects. You have to have a system in order to see the effects of momentum or conservation of momentum. Now, keep in mind, all of this is only true for a closed system. The net external force is 0. So that's an important characteristic when we're looking at momentum and conservation of momentum. It seems pretty clear, or maybe it doesn't, but this idea right here is impulse. Change in momentum is net force times delta time t. And I hope that doesn't run off the board. Doesn't look like it did. Here's my impulse idea. And so the idea of impulse comes from, or is based on Newton's second law. So let's take a look at this in a little bit more detail. So let's begin with looking at conservation of momentum. I guess technically I could have said conservation of linear momentum, because we do have conservation of angular momentum. It should be relatively clear, but I'm just going to refer to it as conservation of momentum. When we're dealing with momentum being conserved, what that means is there is no change in momentum. Going back to just a second ago, this only occurs when the net external force is 0. We can't apply conservation momentum if we have a net force acting on the system of objects. So you have to understand what the system is, and making sure that there's no net force. So let's assume we got this going on. No change in momentum means our initial momentum is equal to our final momentum. We're talking about the system. The initial momentum and the final momentum for the system. So we're adding up all the momenta, I guess, for each object in the system. The typical quote-unquote equation, or the way we like to write the equation, is m1 v1 plus m2 v2 this is my initial momentum for the system. That's equal to m1 v1 prime, the new velocity for mass 1, plus m2 v2 prime, the new velocity for mass 2. This is my final momentum. You can use like VI1, VI2, VF1. It doesn't really matter as long as you differentiate the initial and final velocity for each object. I like to tell the kids that the equal sign is basically our interaction. We have these objects that have a momentum. Something happens. That's the equal sign. Our momentum gets moved around. Our total momentum stays the same. It just moves around a little bit. That's the whole idea of conservation of momentum. Keep in mind, momentum is calculated as mass times velocity. Velocity is a vector, which means momentum is a vector. It could have positive or it can have negative direction. This is key. This is one of the most common mistakes in doing these problems, is that kids forget that the velocity might be a negative. If we got two objects heading towards each other, one of them has to have a negative velocity. So that's very important to drill down and to practice and to think about. Other than that, this is the equation. It just takes time practicing it and plugging in the numbers, identifying where all the different values in the problem go. So let's take a look at the different types. I mentioned the interaction. Let's take a look at the different types of interaction we're going to run into. There are three basic types of conservation of momentum scenarios that we're going to run into. Bodies sticking together. Two objects run into each other and they stick together. In all of these scenarios, you use the same expression, the conservation of momentum expression from just a few minutes ago. What you have to understand here is that we add up the masses and the velocity of both bodies after the collision is the same. So the conservation of momentum expression can be expressed as that. And so they have the same velocity. V1 prime is equal to V2 prime, and I'm going to add up my masses. Bodies sticking together. Or we can have bodies coming apart. The classic scenario of bodies coming apart, maybe two ice skaters are just standing there and they push each other apart and they slide away in opposite directions. The classic scenario for, or I shouldn't say the classic, a possible scenario for bodies sticking together, Spider-Man swinging on his web, swings through the air, grabs somebody off the ground at the last minute. Tarzan swinging down the vine, grabs Jane off the jungle floor right before the lion gets her. Those types of things. Two bodies sticking together. And so bodies coming apart, typically, not always, the initial velocity for both objects is 0. But not always. So I'm gonna go back and I'm gonna use my normal conservation of momentum expression, and if the initial velocity is 0, I just cross out that term. But the two skaters could be sliding together down the ice and then push off. That's perfectly okay. And then bodies bouncing off each other. Billiard balls colliding and they bounce off each other. And here's where you have to use the full conservation of momentum expression. Remember velocity vectors. It tends to be very important on these. It's important in all the problems. More important with that scenario. So these are really the three things that you can have. They come together, they stick, and they might continue moving together. That's the question. They're sitting there and they push each other apart, or they come and they bounce off each other, and we want to see what the various interactions are. So now what I want to take a look at are some terms used a lot with conservation of momentum, and that's talking about inelastic collisions and elastic collisions, talking about the difference, talking about how these scenarios fit into those collision scenarios. I had mentioned that a very common problem that occurs is forgetting that velocity is a vector. Two objects going against each other, one has a negative velocity, forgetting to incorporate that negative sign. Probably an issue that is just as prevalent, if not more, our kids are not fully understanding the two different types of collisions. One type is an inelastic collision, and the other type is an elastic. I kind of understand the confusion. The terms kind of lead themselves to the confusion, but it's very important to understand the difference between the two. With an inelastic collision, momentum is conserved. Again, assuming we have a closed system. With an elastic collision, momentum is conserved. But kinetic energy is also conserved. In elastic collision, we are conserving all our energy. If two things interact and we have an energy loss would be like heat, sound, something deforming. That deformation is a result of energy. Energy is required to do that. It's not an elastic collision. So most of the collisions we deal with in real life and in the problems are inelastic collisions. Bodies sticking together. Always an inelastic collision. Always. Bodies coming apart. Especially if they're just sitting there. If we have two skaters just standing there side by side, they have no velocity, they have no kinetic energy, they come apart, we suddenly have kinetic energy. It had to come from somewhere. That, by the way, is a very good question to test your kids on. When you have two skaters standing there and they're pushing and they come apart by pushing each other, and we have kinetic energy afterwards, none to begin with, where did that energy come from if we have a closed system? Very good question. The problem comes in is they bounce off each other. When two objects collide and then they bounce off each other, it could be an inelastic collision or it could be an elastic collision. Just by knowing they bounce off each other, you can't tell until you ask the question, is kinetic energy conserved? And The only way to know the answer to that question is if the problem doesn't tell you, does the initial kinetic energy of all my objects equal the final kinetic energy? If this equality is true, we have conservation of kinetic energy. It's an elastic collision. The problems dealing with that could be quite complicated. Solving systems of equations. I wouldn't necessarily focus on that more than I would focus more on the idea of what is an elastic collision compared to an inelastic. Again, don't let the terms confuse them. I understand why they think if they bounce off each other, that's an elastic collision, because bouncing balls are elastic. But those are different terms, or those terms are being used in different ways. And so be very careful about that. That can be very confusing. This is a very common problem. So let me look at a couple of other issues that are common with conservation of momentum. Okay, I've already mentioned a couple of the common mistakes with conservation of momentum, but let me just kind of recap them. Velocity vector, very common. Elastic and inelastic collision, understanding the difference. I failed to say the only way to check, I did say the only way to check is typically to compare the initial kinetic energy to the final. If you get that problem and you do check that, and the problems that you get, there's probably no middle ground. It's probably either a clear inelastic collision or it's clearly elastic. And so if you do the calculation on a certain problem, and the difference between initial and final kinetic energy is maybe just a few tenths of a joule out of 10 or 20, it's probably just a rounding issue. If it's going to be an inelastic collision, there's going to be a big difference between the energy before and after. The last issue that I've kind of noticed is that when kids get the problems, and this is when we start looking at things cumulatively, they sometimes have trouble recognizing when to use conservation of momentum versus conservation of mechanical energy. Very, very common issue. And so what I tell them is look for some things in the problem. If we're dealing with multiple bodies, conservation of momentum. If it only tells us the mass of one body and there's only one body within the problem, it's probably going to be conservation of mechanical energy. I always talk about if our height is changing and the speed is changing, it's a conservation of mechanical energy. Typically, with conservation of momentum, it's just our velocity is changing. I get the confusion, I really do. Just reading the problem carefully, we'll get into identifying which approach to take. So that's the idea behind conservation of momentum. I want to take a second and talk about impulse. It's not part of my Unit 6C, but obviously when we're dealing with conservation of momentum, impulse, the change in momentum is a big player. Let's just do a little quick recap on what impulse is, because you really can't talk about momentum and conservation of momentum without looking at impulse also. Let's go back to what Newton's second law is. Net force is the time, rate, and change of momentum. All right. So if we have no net force, no external force, our change in momentum is zero. That's conservation of momentum. Impulse is the change in momentum. So whenever we talk about impulse, we're talking about the object's, how the momentum change of the object. Usually the expression is written as F times delta T. Just rearranging that expression. Now, I know some resources, they give the symbol of J for impulse. I really don't know what J stands for. A jerk. But typically we just talk about delta P. They do use the words impulse and change in momentum interchangeably, so they need to be able to recognize when they're talking about impulse, it's delta P. Keeping in mind that momentum is mass times velocity, and so a change in momentum is also change in mass times velocity. And in the situations that we typically run into, that works out to be mass times change in velocity. And so this is kind of the expression. It's not the whole thing, but it's usually, I think, on the formula sheet, it gives that equality and then includes that. I'm not 100% sure. To keep in mind, time is a scalar, force is a vector, which means impulse or change in momentum is a vector, and that's kind of a weird idea to me, I think. But there is, that means we can have a negative impulse that an object receives. And let's talk about the units real quick. When we're talking about momentum, our units are kilograms times meters per second, which we get units for momentum of kilogram meters per second, which are really weird units. I wish there was a simplified version of that, but there's not. Same units that we get here with change in momentum, which kind of makes sense. If the momentum is changing, it's got to have the same units as momentum. And so change in momentum and momentum have same units. One of the confusing things is if we look at change in momentum as force times time, that's units of Newton seconds. These two unit quantities are the same. A Newton second is the same as kilogram meters per second. So they need to be able to recognize, I usually see Newton seconds when it refers to change in momentum, but not always. So they need to be able to recognize when they're dealing with impulse. So let's look at a situation that comes up often, and let's look at the change in momentum and how it relates to Newton's third law. Remember Newton's third law, every force has an equal and opposite force. No force is alone. Every force has, people express it differently, action, reaction. I'm not a big fan of that, but every force has an equal and opposite force. It occurs at the same time, and equal means it's the same magnitude, opposite direction. So let's say we have object A, and it hits object B. Now, when we're looking at the system, when we look at the AB system, as long as it's closed, there's no external forces, momentum's conserved. We have conserved F net external is 0. That means in the system, no change in momentum for the system. This does not mean the individual objects can experience a change in momentum. What that means is the system will not experience a change in momentum. So when we talk about both objects, that's when conservation of momentum comes into play. But keep in mind, when A hits B, there is a force from A onto B. This force is equal to the force from B on A, according to Newton's third law. It's just in the opposite direction. A hits B this way, B hits A the opposite way. The time that A is hitting B is exactly the same amount of time that B is hitting A. And so what this is telling us is that the change in momentum on A is equal to the change in momentum on B. The magnitudes are equal, but it's in an opposite direction. Don't confuse this by thinking we have no change in momentum in our system. We don't have a change in momentum in the system. We have a change in momentum in the individual objects. Objects A momentum might increase by 5 kilogram-meters per second. Object B's momentum will have to decrease, negative. So we're talking absolute value here. Keep that in mind. And we're talking opposite direction because that's where the vector quantity comes into play. Let's look at a quick impulse example. Somewhat, I don't want to say it's a common example, but it's certainly not unusual. And we have a graph of force as a function of time. And anybody that knows, I love graphs. My favorite. And let's say the graph looks like this. And I tell, first thing you do when you get a graph, you look at the slope. What information does the slope of the graph tell you? Force divided by time. Newtons per second. Those terms, nothing is ringing a bell to me. What's the area tell you? Force times time. Newton seconds. The area is going to be the impulse. Change in momentum. And so let's think about the example that I just looked at. We have object A hitting object B. And this might be a graph of force B experiences. So object B experiences a constant force for some time period. Object B experiences an impulse, a change in momentum. But then the question goes on to talk about what's the change in momentum of object A? And one of the things I want you to pick up on, one of the things to recognize is that the change in momentum of object A is equal to the force applied to object A times the time period that that force was applied for. The force applied to object A, this is the force on object B. And so this is the negative force on object B. And it's real important to recognize that. The time period's the same, but the value, if this is, say, 10 newtons, this value is going to be negative 10 newtons. And that's real important to recognize when we're dealing with impulse problems. A lot of times the information will be for one of the bodies, but the question leads to the other, and you have to recognize the Newton's third law relationship between the two forces. So that's my spiel on my unit 6C, momentum. Hope this was some value. Good luck.